You think atoms are mostly empty space. You've heard it 1,000 times. The atom is 99.99% empty. If you removed all the empty space from all the atoms and all the people on Earth, we'd fit into a sugar cube. The nucleus is like a fly in a cathedral. The electrons are clouds of nothingness orbiting impossibly far away. Your body, this chair, this entire planet, mostly nothing. Empty, void. So here's the question that should bother you. If atoms are mostly empty space, why can't you fall through the floor? Why doesn't your hand pass right through this table? Why does anything feel solid at all? Think about it. Your hand is mostly empty space. The table is mostly empty space. When you push down on it, empty space is meeting empty space. So what's stopping you? What's doing the pushing back? Most people have never really thought about this. They just accept it. Atoms are empty, but somehow things are solid. That's just how it is. But that's not an answer. That's just repeating words. When you really ask what's stopping your empty hand from passing through an empty table, when you dig into what's actually happening, you discover something so strange, so fundamentally different from anything you experience in everyday life, that it changes everything you think you know about what solid even means. Let me show you what I mean. Go back to the early 1900s. Nobody knew what atoms looked like. They knew atoms existed, they knew matter was made of tiny particles, but the structure, complete mystery. Then came Ernest Rutherford. Rutherford wanted to probe the atom, see what's inside. So he did something clever. He took a radioactive source that spits out alpha particles. These are heavy, fast-moving particles. He aimed them at a thin sheet of gold foil, and he put detectors all around to see where the alpha particles went after hitting the gold. His expectation was simple. If atoms are like little blobs of matter, the alpha particles should pass right through with maybe a little deflection, like shooting bullets through fog. Most go straight, some get nudged slightly. That's what he expected. That's not what happened. Most alpha particles did go straight through, but some, a tiny fraction, bounced back, straight back, like they hit something solid. Rutherford was shocked. He said it was like firing a cannonball at tissue paper and having it bounce back and hit you. What could cause that? There's only one explanation. Almost all the mass of the atom is concentrated in a tiny, tiny region at the center, the nucleus. And the rest? Empty. The electrons are somewhere out there, far away. How far? The nucleus is about 10 to the minus 15 meters across. The atom itself is about 10 to the minus 10 meters across. That's 100,000 times bigger. If the nucleus were the size of a marble, the atom would be the size of a football stadium. And the electrons? They're orbiting somewhere in the outer seats. Everything in between? Nothing. Empty space. So Rutherford discovered the atom is mostly empty. That's where that idea comes from. And it's true. The nucleus is incredibly small. The electrons are far away. But here's the thing. Rutherford's picture was incomplete. He imagined electrons orbiting the nucleus like planets orbiting the sun, tiny particles going in circles. And if that were true, if electrons really were tiny particles orbiting far away, then yes, atoms would be mostly empty and you should fall through the floor. But electrons are not tiny particles orbiting the nucleus. That picture is wrong, completely wrong. And that's where everything gets strange. Let's talk about electrons. You think of an electron as a particle, a tiny little ball, somewhere in the atom, orbiting. But that's not what an electron is. An electron is not a particle in the way you think of particles. It's not a little ball sitting somewhere. An electron is a quantum object. And quantum objects don't have definite positions. They exist in a cloud of probability. Let me say that again because it's important. The electron is not at a specific location orbiting the nucleus. The electron is everywhere in the atom at once. It's smeared out. It's a wave, a cloud, a probability distribution. You can't say the electron is here. You can only say there's a probability of finding it here if you look. And that cloud, that wave function, fills the entire atom. The electron isn't far away from the nucleus, leaving empty space in between. The electron is everywhere in that space simultaneously. The atom is not empty. It's filled with electron cloud. But even that's not the full answer. Because, okay, the electron is a cloud filling the atom. Fine. But a cloud is still mostly empty, right? A cloud of water vapor is mostly empty space with a few water molecules floating around. So why can't you pass through it? Here's where we need to talk about forces. When you push your hand down on a table, what's really happening? You think the atoms in your hand are touching the atoms in the table. But atoms don't touch. Not in the way you think of touching. There's no contact. No physical collision of surfaces. What's happening is forces. Electric forces. Electromagnetic repulsion. Let me explain. Every atom has a nucleus with protons. Protons are positively charged. And every atom has electrons. Electrons are negatively charged. Opposite charges attract. Same charges repel. That's electromagnetism. Now, when your hand gets close to the table, the electrons in your hand get close to the electrons in the table. Both are negatively charged. They repel strongly. The closer they get, the stronger the repulsion. This repulsion is what you feel as solidity. The table is not pushing back because it's solid in the sense of being a continuous lump of matter. The table is pushing back because the electrons in the table are repelling the electrons in your hand with enormous electromagnetic force. You've never touched anything in your entire life. Not this screen, not another person, not even yourself. Every time you think you're touching something, you're feeling electromagnetic repulsion. The electrons in your hand repel the electrons in the object. That repulsion is what you interpret as the feeling of touch. You're not touching, you're being repelled. Always. Everything you've ever felt, every sensation of contact, is electromagnetic force pushing you away. The floor is not holding you up because it's solid. The floor is holding you up because the electrons in your feet and the electrons in the floor repel each other so strongly that you can't get closer. You're hovering. Always hovering, floating on a cushion of electromagnetic repulsion so strong it feels like solid ground. But now we're getting to the deeper question. Why is that repulsion so strong? Why doesn't your hand just push through? After all, electromagnetic force follows an inverse square law. The closer you get, the stronger it gets. Yes, but forces can be overcome. You can push harder. You can apply more force. So why can't you push hard enough to make your hand go through the table? Why doesn't the repulsion just slow you down but still let you pass through if you push hard enough? And here's where quantum mechanics comes in with something truly bizarre. Something called the Pauli exclusion principle. Wolfgang Pauli discovered something strange about electrons. Two electrons cannot be in the same quantum state at the same time. Let me say that more carefully. Every electron has a set of quantum numbers that describe its state, its energy level, its orbital shape, its spin. And Pauli discovered that no two electrons in the same system can have the exact same set of quantum numbers. If one electron is in a particular state, no other electron can be in that state. They're excluded. Now, why does this matter for solidity? Because of what happens when atoms get close. When your hand approaches the table, the electron clouds start to overlap. The electrons in your hand start occupying the same space as the electrons in the table, but they can't occupy the same quantum states. They're forced into higher energy states, states they don't want to be in. And moving to a higher energy state requires energy, a lot of energy. This creates an enormous resistance. It's not just electromagnetic repulsion. It's quantum mechanical exclusion. The electrons literally cannot overlap without a huge energy cost. And that energy cost is what makes matter impenetrable. This is called degeneracy pressure. It's not a force in the traditional sense. It's a consequence of quantum statistics. Electrons resist being in the same state. And when you try to compress matter, when you try to push atoms closer together, you're forcing electrons into states they're excluded from. And the universe says, no, not without enormous energy. This is why you can't fall through the floor. Not because the floor is solid in some continuous material sense, but because the quantum states of the electrons in your body and the quantum states of the electrons in the floor cannot overlap. The Pauli exclusion principle forbids it. You are held up by quantum mechanics. Let me give you an analogy. Imagine a concert hall with assigned seating. Every seat has a number. Every person has a ticket. And the rule is you can only sit in your assigned seat. No two people can sit in the same seat. Now, what happens if more people show up than there are seats? You can't fit them in. Not because of physical space exactly, but because the rule forbids two people in one seat. The only way to fit more people is to add more rows, higher up, which costs money and effort. That's what happens with electrons. They're all trying to be in the lowest energy states. But the Pauli exclusion principle says only so many can fit. When you try to compress matter, you're trying to add more electrons to states that are already full. And the only way to do that is to put them in higher energy states, which requires enormous energy. That's degeneracy pressure. Now here's where this gets truly wild. This quantum pressure, this Pauli exclusion principle, is what holds up not just tables and floors, but stars. When a star runs out of nuclear fuel, gravity tries to collapse it. The star wants to shrink. All that mass pulling inward, what stops it? For smaller stars, electron degeneracy pressure. The electrons are packed so tightly that they can't be compressed further without violating the Pauli exclusion principle. The star becomes a white dwarf, a dead star held up not by nuclear reactions, not by heat or pressure in the normal sense, but by quantum mechanics. The same principle that keeps you from falling through the floor is holding up the corpses of stars. And if the star is too massive, even electron degeneracy pressure isn't enough. Gravity wins. The electrons get crushed into the protons, forming neutrons. Now you have a neutron star. And what holds that up? Neutron degeneracy pressure. Same principle. Neutrons also obey the Pauli exclusion principle. They can't all occupy the same state, so the neutron star resists further collapse. A teaspoon of neutron star material weighs 1 billion tons. Not because the neutrons are heavy, because they're packed so tightly that quantum mechanics is screaming no. The universe is resisting. And if the star is even more massive, not even neutron degeneracy pressure can stop it. Gravity overcomes quantum mechanics. The star collapses into a black hole. But for most stars, for white dwarfs and neutron stars, it's quantum mechanics that holds the line. The Pauli exclusion principle is the last defense against gravitational collapse. So let's bring this back to your hand and the table. You're not falling through the floor because electrons refuse to occupy the same quantum states. The electromagnetic repulsion pushes back, yes. But the deeper reason, the fundamental reason you can't push through, is quantum mechanics. The Pauli exclusion principle creates a wall, not a physical wall, a quantum wall. And that wall is absolute. You cannot pass through it without adding enormous energy. More energy than your muscles can provide, more energy than anything in your everyday experience can provide. So you stay on the surface, you feel solidity, but it's an illusion, not in the sense that it's fake. The force is real, the resistance is real, but the reason for it is nothing like what you think. You're not resting on solid matter. You're being held up by quantum statistics. Now here's something even stranger. Let's talk about what empty space actually means. You think of empty space as nothing, vacuum, void, but quantum mechanics says that's wrong too. Even empty space isn't empty. There's something called the quantum vacuum, and it's full of activity. Virtual particles constantly pop in and out of existence. pairs of particles and antiparticles appearing for the briefest instant, then annihilating each other and disappearing. They borrow energy from nothing, exist for a moment, then pay it back. This happens everywhere, all the time, even in the emptiest regions of space. The vacuum is seething with these quantum fluctuations. So when you remove all the matter, all the atoms, you don't get nothingness. You get quantum foam, a bubbling, fluctuating field of potential. Empty space is not empty. It's full of fields, electromagnetic fields, quantum fields. These fields are always there, always vibrating, always ready to create particles if given enough energy. And here's the thing. The electrons and atoms, the electrons that create solidity, they're not separate from these fields. Electrons are excitations in the electron field. They're ripples, waves. When you see an electron, you're seeing a disturbance in a field that fills all of space. The electron isn't a little ball sitting in empty space. The electron is the space itself, vibrating in a particular way. This is quantum field theory, and it tells us that particles aren't fundamental objects. Fields are fundamental. Particles are just what happens when fields get excited. So the atom isn't mostly empty space with a few particles floating around. The atom is a region where multiple fields, the electron field, the quark fields that make up the nucleus, are all excited in a particular configuration. The whole thing is fields, all the way down. Let me give you another example to make this concrete. You've probably heard of the Heisenberg uncertainty principle. It says you cannot know both the position and momentum of a particle with perfect precision. The more precisely you know where something is, the less precisely you know how fast it's moving, and vice versa. This isn't a limitation of measurement. It's not that we're just bad at measuring. It's that the particle doesn't have a definite position and momentum simultaneously. They're fundamentally uncertain. Now, why does this matter for empty space? Because if an electron had a definite position, if it were sitting still in a definite location, we would know both its position exactly and its momentum, which would be zero. That violates the uncertainty principle. So the electron can't sit still. It has to be spread out. It has to be moving, jiggling, fluctuating. This is called zero-point energy. Even at absolute zero temperature, even in the ground state, quantum systems still have motion. They can never be perfectly still because that would violate uncertainty. So the electron in an atom is always moving, always spread out, always uncertain. And that uncertainty, that quantum jitter, is part of what gives the atom its size. In fact, you can calculate the size of an atom using the uncertainty principle. The electron is bound to the nucleus by electromagnetic attraction. It wants to get close. But if it gets too close, its position becomes very well defined, which means its momentum becomes very uncertain, which means it has high kinetic energy. That energy costs. So there's a balance. The electron settles into the lowest energy state, where the attraction to the nucleus is balanced by the cost of confining it to a small region. And that balance determines the size of the atom. About 10 to the minus 10 meters. Not because the electron is orbiting at that distance, but because that's where the quantum uncertainty balances the electromagnetic force. The atom size is a quantum effect. Remove quantum mechanics, and atoms would collapse. Electrons would spiral into the nucleus. Matter as we know it couldn't exist. So let's put all this together. The atom is mostly empty space in the sense that the nucleus is tiny and the electron cloud is large. But the electron cloud is not empty. It's filled with the electron's wave function, the probability distribution of where the electron might be found. And when atoms come close, their electron clouds overlap, and the Pauli exclusion principle kicks in, creating enormous resistance. That resistance is what you feel as solidity. But it's not because the atoms are solid objects bumping into each other. It's because quantum mechanics forbids the electrons from occupying the same states. And underneath all of this, even the empty space between the nucleus and the electrons isn't truly empty. It's filled with quantum fields, fluctuating vacuum energy, virtual particles popping in and out of existence. The whole picture of matter as solid objects sitting in empty space is wrong. Matter is excitations in quantum fields. Space is not empty. And solidity is electromagnetic repulsion plus quantum exclusion. Now, you might be thinking, okay, but we can compress things. We can squeeze matter. We can apply pressure and make things smaller. So clearly the resistance isn't absolute, right? And you're right. You can compress matter, but not by much. And the amount of energy required increases rapidly. When you compress a gas, you're pushing atoms closer together. The electromagnetic repulsion increases. You have to do work. When you compress a solid, you're trying to squeeze atoms even closer. The electron clouds resist. The degeneracy pressure fights back. And there's a limit. You can only compress so far before the energy cost becomes astronomical. For ordinary matter, like the floor or a table, you're already at the limit. The atoms are packed as tightly as they can be at normal pressures. You can't push them closer without enormous force. That's why the floor feels solid. You're already at the quantum limit. And here's a beautiful example of this. Diamonds. Why are diamonds so hard? Because the carbon atoms are arranged in a very tight, rigid lattice. The electron clouds are overlapping as much as they can while still obeying the Pauli exclusion principle. Any attempt to compress the diamond further, to squeeze the atoms closer, runs into massive quantum resistance. The hardness of diamond is not because carbon atoms are special. It's because of how they're arranged and how the quantum mechanics of electron clouds resists further compression. You're feeling quantum mechanics when you try to scratch a diamond. The resistance you feel is the Pauli exclusion principle saying no. Now let's talk about something really strange. Tunneling. If the quantum resistance is so strong, if the Pauli exclusion principle forbids electrons from overlapping, how is it that particles can sometimes pass through barriers? You've probably heard of quantum tunneling. A particle on one side of a barrier that it doesn't have enough energy to climb over can sometimes appear on the other side. It tunnels through. How? Isn't that exactly what we said can't happen? Isn't that falling through the floor? Not quite. Tunneling happens because the particle's wave function extends into the barrier. There's a small probability of finding the particle on the other side. The particle doesn't travel through the barrier in the classical sense. It doesn't push through. The wave function is already on both sides, and when you measure, you might find the particle on the far side. It's not violating the Pauli exclusion principle. It's not occupying the same state as another particle. It's just that the wave function, the probability cloud, extends beyond where you'd classically expect. Tunneling is crucial to how the world works. Nuclear fusion in the sun happens because protons tunnel through the electromagnetic barrier that should keep them apart. They don't have enough energy to overcome the repulsion classically. But quantum mechanically, there's a probability they get close enough to fuse. And over billions of years, with countless protons colliding, tunneling happens often enough to power the sun. Radioactive decay happens because particles tunnel out of the nucleus. They're trapped by the nuclear force, but there's a small probability they appear outside. And eventually, they do. Tunneling is real. But it's not the same as macroscopic objects passing through each other. Your hand can't tunnel through the table because your hand is made of trillions of atoms. For all of them to simultaneously tunnel would require an absurdly improbable alignment of quantum events. The probability is so small that it will never happen. Not in the lifetime of the universe. Not in a trillion lifetimes. So while individual particles can tunnel, bulk matter cannot. There's another aspect to solidity I need to mention: chemical bonds. When atoms come together to form molecules or solids, they share electrons. The electrons are no longer confined to individual atoms. They're spread across multiple atoms. This is a chemical bond, and these bonds have specific energies, specific configurations. Breaking a bond requires energy. When you try to pull atoms apart, you're fighting against the chemical bonds. When you try to bend or deform a solid, you're stretching or compressing bonds, and the bonds resist. They have equilibrium lengths and angles. Deviate from those, and you store energy. Release your hand, and the bonds snap back, releasing that energy. This is elasticity, the springiness of matter. And it's all electromagnetic. The bonds are electrostatic attractions between electrons and nuclei, balanced by electron-electron repulsion and Pauli exclusion. Everything comes back to quantum mechanics and electromagnetism. So here's the full picture. The atom is mostly empty in the sense that the nucleus is incredibly small and far from the electron cloud. But the space isn't empty. It's filled with the electron's wave function and quantum fields. When atoms interact, electromagnetic forces and the Pauli exclusion principle create resistance. That resistance is what you experience as solidity. The floor holds you up, not because it's a continuous solid substance, but because the quantum states of the electrons in your body cannot overlap with the quantum states of the electrons in the floor. Chemical bonds between atoms create additional structure and resistance. And all of this, the size of atoms, the strength of bonds, the impenetrability of matter, comes from quantum mechanics. Remove quantum effects, and matter collapses. The world as you know it ceases to exist. Now, let's think about what this means for everyday experience. You walk on the ground, you sit in a chair, you pick up objects. Every single one of these experiences is mediated by forces you can't see acting on particles that aren't where you think they are. The solidity you feel is quantum exclusion. The texture is electromagnetic interaction. The weight is gravity pulling you into a floor that resists with quantum pressure. None of it is what it seems. And yet, it's completely predictable. We can calculate exactly how strong these forces are. We can predict how materials will behave. We can engineer structures, knowing precisely how much force they can withstand, all from quantum mechanics and electromagnetism. The fact that we can take these bizarre, counterintuitive principles and use them to build bridges and design microchips and predict the properties of materials is extraordinary. The universe is strange, but it's comprehensible. And here's the beautiful part. Once you understand this, once you see that solidity is quantum exclusion and electromagnetic repulsion, you start to see the connections everywhere. Why metals conduct electricity? Because some electrons are free to move through the lattice. Why insulators don't? Because the electrons are tightly bound. Why some materials are transparent? Because photons pass through without being absorbed. Why others are opaque? Because the photons interact with the electron clouds and get absorbed or scattered. Every property of every material comes down to how electrons behave in that structure. And electron behavior is quantum mechanics. The whole world, everything you touch, everything you see, is quantum mechanics in action. So why can't you fall through the floor? Because the electrons in your body and the electrons in the floor obey the Pauli exclusion principle. They refuse to occupy the same quantum states. And that refusal creates a force, a resistance, a pressure so strong that it holds you up. You are floating on a sea of quantum mechanical impossibility. Every step you take, you're being repelled by forces you never see, held up by principles you don't consciously think about, prevented from falling by the fundamental structure of reality itself. The floor is not solid in the way you imagine, but it's solid in a way that's far stranger and far more beautiful. It's solid because the universe says two electrons cannot be in the same state. And that simple rule, that one principle, is enough to create everything you experience as the physical world. That's the answer. And it changes how you see reality.